In this video we're going to look at how to solve simultaneous first order differential equations by creating a second order differential equation. So we're going to have two equations with three variables. We've got the independent variable t, and we've got dependent variables x and y. So x and y are functions of t. And we're going to know that the rate of change is connected to x, y and t by a relationship of the form dx by dt equals a constant times x plus another constant times y plus a function of t. And then similarly, the rate of change of y, dy by dt, is going to be equal to a constant times x plus another constant times y plus some function of t. So the example that we're going to look at in this video is going to be, we've got variables x, y and t are linked by the equations dx by dt equals minus x minus 2.5y plus 11.5. dy by dt is equal to 10x minus y minus 37. And we've got the initial conditions that x equals 6 and y equals 3 when t equals 0. And the first part of the question is going to ask us to prove that x must satisfy the second order differential equation d2x dt squared plus 2 times dx by dt plus 26x equals 104, with initial conditions that when t equals 0, x equals 6 and dx by dt is minus 2. So what we need to do is we start off with the dx by dt equation. Now we're being asked to find a second order equation for x, so the obvious thing to do is to obtain a d2x dt squared term by differentiating equation 1. So differentiating equation 1, we get d2x dt squared equals minus dx by dt minus 2.5 dy by dt plus the derivative of 11.5, which is just 0. Now, the first thing we're going to try and do is eliminate the dy by dt term. So we can do that making use of equation 2. So we're going to substitute for dy by dt in equation 3. So that will now give me d2x dt squared equals minus dx by dt minus 2.5 lots of 10x minus y minus 37. In other words, we've got d2x dt squared plus dx by dt plus 25x equals 2.5y plus 92.5. Now at the moment we've still got y appearing in equation 4, but we can get rid of that by using equation 1. So looking at equation 1, we can see that equation 1 tells us that dx by dt is minus x minus 2.5y plus 11.5. So that tells me now that 2.5y is minus dx by dt minus x plus 11.5. Or in other words, we've got y is 0.4 times by minus dx by dt minus x plus 11.5. And we can now substitute this into equation 4 so to get rid of the y term. So if we do that, we've now got d2x dt squared plus dx by dt plus 25x is 2.5 times 0.4, which conveniently comes out in this case just to be 1, times by minus dx by dt minus x plus 11.5 add the 92.5. So we've got d2x dt squared plus dx by dt plus 25x is equal to minus dx by dt plus minus dx by dt minus x plus 11.5 plus 92.5. Bringing all of the x terms over to the left-hand side, we've got d2x dt squared plus 2 times dx by dt plus 26x equals 104. So we've obtained the differential equation that we were being asked to obtain. We've still got to just check on the initial conditions. So when t equals 0, we're told that we know that x equals 3 and x equals 6 and y equals 3. So making use of equation 1, we've got dx by dt is minus 6, take away 3 times 2.5, which is 7.5, add 11.5, so that gives me dx by dt equals minus 2. So we have got the initial conditions that when t equals 0, x is 6 and dx by dt is minus 2. So we've now done part A of the question. So moving on, we've now got to find expressions for x and y in terms of t. Well, we've got the differential equation, a second order differential equation for x, so we can solve that in the methods of a previous video. So we start off by trying to find the complementary solution. So that is, we try and solve the equation d2x dt squared plus 2 dx by dt plus 26x equals 0. That has an auxiliary equation of m squared plus 2m plus 26 equals 0. The roots of that quadratic equation are m equals minus 1 plus or minus 5i. So the complementary solution is x equals e to the minus 1 times t, in other words just e to the minus t, times by a cos 5t plus b sin 5t, where a and b are constants. For the particular solution, we could try just x equals k, and if we've got x equals k, then dx by dt is 0 and d2x dt squared is equal to 0. So d2x dt squared plus 2 dx by dt plus 26x will just equal 0 plus 0 plus 26k, and that will equal 104 if k is 4. So we've got a particular solution of x equals 4. So we've now got a general solution of the differential equation of x equals 4 plus e to the minus t times by a cos 5t plus b sin 5t. But we want the solution that gives me that x equals 6 and dx by dt equals minus 2 when t equals 0. So we've got a little bit more work to do before we've got the expression for x. So we've got the general solution there. So when t equals 0, we know that x has got to equal 6. So that tells me that 6 has got to equal 4 plus 1 times a times 1 plus b times 0. In other words, that gives me 6 equals 4 plus a. So I've got a equals 2. Using the product rule to differentiate the expression for x, we've got dx by dt is equal to 0, that's the derivative of 4. Derivative of e to the minus t is minus e to the minus t times by the a cos 5t plus b sin 5t left alone, plus e to the minus t times by the derivative of the bracket, and the derivative of the bracket is minus 5a sine 5t plus 5b cos 5t. Now, when t equals 0, we want dx by dt to equal minus 2. Now, when t equals 0, cos 5t is 1, sine 5t is 0, so what I've got is minus 2 has got to equal minus a plus 5b. But we already know that a is 2, so the fact that I've got minus a plus 5b has got to equal minus 2 tells me I've got minus 2 plus 5b equals minus 2, so b is 0. So I've now got my required solution, which is x equals 4 plus 2 e to the minus t cos 5t. And we also know that dx by dt is equal to minus 2 e to the minus t cos 5t minus 10 e to the minus t sine 5t. Earlier on, we've discovered that rearranging the very first equation, we've got 2.5y is equal to minus dx by dt minus x plus 11.5. So that gives me 2e to the minus t cos 5t plus 10e to the minus t sine 5t. That's the dx by dt bit. Take away x, which is 4 plus 2e to the minus t cos 5t plus 11.5. Tidying that up, we've got 2.5y is 10e to the minus t sine 5t plus 7.5. In other words, we have y is equal to 3 plus 4e to the minus t sine 5t. So we've now found expressions for x and y in terms of t. So there are expressions. Describe the behaviour of the point xy as t tends to infinity. Well, as t tends to infinity, e to the minus t tends to 0, so the value of x must get closer and closer to 4, the value of y must get closer and closer to 3, so the point xy is going to get closer and closer to the point 4, 3. And the little video here actually will show us the motion of the point P as t varies from 0 to 10. So if we just play the video. So we're animating the value of t, and you can see that as t is increasing, we're getting closer and closer to the point 4, 3. And now we've just got a repeat of the first few seconds of the motion. So we've introduced the method of solving the simultaneous differential equations. What you'll need to do now is go away and try to use this method on a couple of examples.